Welcome back again, section 4.1. We're going to finish up section 4.1 with the first derivative test and talking about relative extrema. When we talk about relative extrema, we're talking about the relative maximum and relative minimum. Again, we've talked about these in Algebra 2. We've talked about them in pre-calculus. Where do those relative maximum and minimums occur, and how does it happen? If I go back to a cubic, and it can be any kind of function we want, but if I give you this example as a cubic here, we notice that we have these critical values, these critical points that we talked about when f prime of x equaled 0. F prime of x equals 0. Well, what do we notice about this point, this critical point, and this critical point? Well, relative means, within this general region, this is going to be our highest point. So we see that we have a relative maximum here when f prime of x equals 0. And we have a relative minimum, so in general, we have relatively in this space, we say that we have a relative minimum, or the lowest point in that region. Again, both where f prime of x equals 0. Well, what's different about these 2 points? To the left of this graph, we see that we have increasing intervals. And on the right side of this relative max, we see we have decreasing intervals. So we went from an increasing to a decreasing portion of our graphs. Again, the derivatives were increasing. The slopes of the tangent lines were positive. And here the slopes of the tangent lines are negative. Likewise, or similarly, around this relative minimum, we see a negative slope, and then we turn into a positive slope. So it goes from negative to positive. So if you think about it, if we go from a positive slopes, or increasing function, to a decreasing function, we're always going to have a high point, aren't we? If we go from a decreasing portion of the function to an increasing portion of the function, we're going to see that we have a relative minimum. And we can do this as many times as we want. And we'll always see that we go from increasing to decreasing for a relative max, and a decreasing to increasing for a relative min. So our critical information that we want to see today is that f prime of x changes from positive to negative at a critical point, then f of x is going to be a relative maximum at that point. Likewise, or similarly, f prime of x changes from negative to positive, then we have a relative minimum at that point. So how are we going to find this critical information, these relative maximas and minimas? Well, what we can do, again, we're going to find those critical values. We're going to find that first derivative. First derivative is going to be here, 2x plus 3. We're going to set that equal to 0, again, because we're going to figure out when the first derivative equals 0 to see if we have a maximum or a minimum point. Those are critical points. In this case, solving for x, I get negative 3 halves. I'm going to go up and set up my intervals. So I'm going to go from negative infinity to negative 3 halves, and then negative 3 halves to infinity. I'm going to go ahead and create my test values. From negative infinity to negative 3 halves, I can go ahead and test, let's say, negative 2. Negative 3 halves to infinity gives me 0. I'm going to go ahead and find the sign of f prime of x. So then negative 2, and plug it in. 2 times negative 2 gives me a negative 4, plus 3 gives me a negative. And if I plug in 0, 0 plus 3 gives me a positive, doesn't it? So I go from a decreasing interval to an increasing interval. So again, I'm going decreasing and then increasing. And that makes sense to me since I have an x squared. I know I have a quadratic. It's going to be in the shape of a u. My a value, my leading coefficient, is positive. So I'm going to be opening up. So I should, as I think about my polynomials and my characteristics of them, see that we have a minimum value. So we say that we have a relative minimum when x equals negative 3 halves. We can take this a step farther and say that it is, well, how do I know what it is? Well, if I take negative 3 halves and plug it into my original function, remember what's going to happen if I take negative 3 halves and plug it into my derivative, I'll get 0 out. And I'll always get 0. That's not my information I'm looking for. I want to know what is that relative minimum. So if I take negative 3 and plug it in to my x value, we'll do them up here. I get negative 3 halves squared plus 3 times negative 3 halves plus 8. So doing a little bit of math there, we get 9/4 minus 9 halves plus 8. Go ahead and find a common denominator. We get 9/4 minus 18/4 plus 32/4. So I get a negative 9/4 plus 32/4. My equal sign in there, I guess. So I get a positive 23/4. And that gives me what my relative minimum is. So I have a relative minimum when x equals negative 3 halves. It is 23/4. So there's my x value, there's my y value. Or I could say the relative minimum occurs at the point negative 3 halves and 23/24, or 23/4, sorry. So a lot of different things that we can ask and that you should be able to come up with at this point in time. So relative minimum when x equals negative 3 halves. The relative minimum is 23/4. It occurs at that point. Now, a little side note of this, and as you get into your higher level of calculuses and take calculus in college there, we're also going to see that this is a global minimum. Because we know the characteristics of a polynomial, of a quadratic polynomial in this manner, we're never going to be lower than that vertex. So we can also actually say that this is a global maximum or a absolute maximum. We'll talk about those as the days come through here. So we can also do this with our radicals and our rationals and anything of that sort. So let's go ahead and talk about a rational here. Again, we're going to find our first derivative. Looks like here we have a quotient rule. So we have x plus 1 times 1 minus x times 1 divided by that denominator squared, which is x plus 1 squared. We're going to go ahead and clean that up. Well, x plus 1, it gives me x plus 1 minus x, so I get 1 divided by x plus 1 squared. Go ahead and set that equal to 0. Again, remember, as I look at a rational, I set the numerator equal to 0. I'm going to set my denominator equal to 0. 1 equals 0, that doesn't make sense to me. X plus 1 squared equals 0, so I get x equals a negative 1. So my intervals, I only have 2 intervals. I'm going to start at negative infinity and go to negative 1, and then negative 1 to infinity. My test values, I'm going to plug in negative 2, and I'm going to use 0. And I'm looking at the sign of f prime of x. So take negative 2 and plug it in. Again, I'm going to plug it in on here. My top number is always going to be positive, isn't it? 1 is always going to be positive. The bottom, x plus 1 squared, that's always going to be positive as well. So it doesn't matter if I plug in negative 2 or 0, I always get a positive value out of my denominator. So I've got increasing, and then I've got increasing. What does that mean? Remember, for us to have a relative extrema, a relative max, or relative min, I have to have a change in my signs. In this case, I don't have it. I have increasing to increasing. So I know there is no relative extrema. No relative extrema for this function. And again, as we get into curve sketching, we're going to look at this problem again. We're going to talk about, well, why didn't that have a relative extrema? What's happening at x equals negative 1? That was the only value that could happen, right? Because that's what our interval broke at. If I come back to the original, if I plug in negative 1, I get negative 1 over negative 1 plus 1, which is 0. Negative 1 divided by 0, asymptote. We'll be getting to asymptotes very, very soon here. So we can't have a relative extrema on an asymptote, can we? All right, our last one today, we have a quintic function here. So we're going to go ahead and find our first derivative. We can do this with higher exponent as well. We picked this one just to have a little bit of fun with it. Our derivative is 15x to the fourth minus 60x to the second. I'm going to go ahead and set that equal to 0. I'm going to factor out my common factor, which is 15x squared. That gives me x squared minus 4 equal to 0. Go ahead and factor out that x squared minus 4, or you can do a square root method. Doesn't matter to me as you solve it. But we should see x equal to 0 and plus or minus 2. So if I set up my intervals, I go from negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. Notice these can get on the lengthy side, can't they? Yeah. So what do we want to test? So if I want to test negative infinity to negative 2, I'm going to test negative 3. Negative 2 to 0, I'm going to test negative 1. 0 to 2, 1, and 2 to infinity is going to be 3. I'm looking at the sign of f prime of x. If I look at my function, again I'm going to look down here. My first term is always positive, 15x squared. So I can start out being a positive on all of these, if you want. So that x plus 2 and x minus 2, or x squared minus 4, doesn't matter. Maybe we'll come up here, won't we? That makes a little more sense. We don't have to plug in so much. So negative 3 squared is 9. 9 minus 4 is a positive. Negative 1 squared is 1 minus 3. That's a negative. 1 minus 4 gives me a negative. And 9 minus 4, when I plug in 3, that gives me a positive. So I'm increasing, then I have a decreasing, another decreasing, and then an increasing. So let's go ahead and think about what's happening here. Again, if I change from increasing to decreasing, so if I go increasing to decreasing, I have a relative max. Decreasing to decreasing, well, that doesn't make any sense to be a relative min or a max, does it? Because I'm decreasing and then I decrease and I continue to decrease. There's no curvature there. So I have nothing here. Nada. Nothing. None. Decreasing to increasing. So there I'm going to decrease and then I'm going to increase. Decrease to increase. I have a relative minimum. So I know my relative max is going to be, relative max at x equals negative 2, and a relative minimum at x equals 2. Again, if I ask you what that relative max or relative min is, we would take these values and plug them back into the original function. Or if I ask you what the point was, we'd have to come back again to get the y value out of the original function. We normally do that with some of the smaller exponents, x to the fifth. We should be able to know what x to the fifth or 2 to the fifth is, though we're going to not make you do that at this point in time. So there, excuse me, that gives you an idea of our relative maxes and minimums. Good luck as I go get a drink of water.